Hey everyone, let's just jump right in. If you've ever found yourself wondering how exactly artificial intelligence actually learns, looking past all the flashy buzzwords, well, you're definitely in the right place. Today, we're popping the hood on AI. Using the AI field guide as our map, we're going to break down the actual mechanics of neural networks. And don't worry, we're doing this intuitively, completely skipping the heavy math.
Here's our roadmap for this explainer. 1. Anatomy of a neural network. 2. Activation functions, the spark. 3. The heartbeat of training. 4. Loss functions and optimizers. And 5. Preventing AI from memorizing.
Let's kick things off with Section 1, Anatomy of a Neural Network.
Okay, let's build our digital brain from the ground up. To make this massive concept feel a bit more real, I want you to picture a giant mixing board in a recording studio. Except, imagine this mixing board is literally the size of Manhattan. A model's knowledge is really just billions of these adjustable mathematical knobs, which we call weights. So when you hear someone say a modern large language model has hundreds of billions of parameters, they just mean it has hundreds of billions of these single floating point numbers. Training, in a nutshell, is just turning those knobs over and over until the model's output perfectly matches what we want.
Basically, a neural network is set up like a digital assembly line. It's a stack of layers, and each layer is made up of individual neurons. Every single neuron follows a super simple, repetitive sequence. First, it takes the outputs from the previous layer, multiplies each one by a weight, and sums them all up. Simple enough, right? Then, it adds another learned number called a bias, applies a mathematical function to it, and passes that result forward. This whole process just cascades continuously, starting at the input layer, running through the hidden layers in the middle, and finally landing at the final output prediction.
Moving on to Section 2, Activation Functions, the spark.
Now, here's the catch. If our network only multiplied and added numbers, it would really just be a glorified linear calculator. It would be completely incapable of grasping complex things like language or images. In fact, stacking layers would be totally pointless, because the whole network would just collapse into one giant straight line. The absolute game changer here is the activation function. It provides this crucial, nonlinear spark. It's basically the mathematical kink that allows the network to break out of straight lines and actually start understanding the messy, complex, nonlinear patterns of the real world.
It's actually pretty fascinating to look at how the menu of these nonlinear ingredients has evolved over time. You've got older functions like sigmoid and tan, which neatly squish numbers down into specific ranges. Then there's ReLU, which just outputs the maximum of 0 or x. It's fast, it's simple, and it works wonderfully in those hidden layers. Now, if you need a probability distribution where the outputs all sum to 1, say if the model is trying to choose the next word in a sentence, you'd use softmax. But for the absolute frontier models today, like Llama and modern LLMs, a function called swiglu is the standard. And hey, while you might rarely pick these yourself if you're just prompting an existing model, they are absolutely the secret sauce if you're ever building an architecture from scratch.
All right, Section 3, the heartbeat of training.
So now that we've got the static anatomy of our network laid out, let's look at the dynamic engine that actually brings it to life. Training a model is an incredibly repetitive process, and it really all boils down to 4 sequential steps. Think of this as the heartbeat. Step 1, the forward pass. Step 2, calculating the loss. Step 3, the backward pass. And Step 4, gradient descent.
Let's look at that in motion. During the forward pass, a batch of input data flows through the network to make a guess, a prediction. Next, we calculate the loss, which is just a number showing exactly how wrong that guess was. Then comes the real magic, backpropagation. During the backward pass, the model uses calculus to work backwards and figure out exactly how much every single weight contributed to that error. And finally, we hit gradient descent. Imagine you're trying to walk down a mountain, but you're totally blindfolded. You'd probably feel the slope with your feet and take a tiny step downhill, right? That's exactly what the model is doing, nudging the weights slightly in the direction that reduces the error for next time. This entire loop processes a small batch of data and repeats millions of times using a method called stochastic gradient descent.
Which brings us to Section 4, loss functions and optimizers.
Now that we can see the engine running, let's dig into the specific tools used to actually tune the machine. When we measure how wrong a model is, we use a loss function. Simple rule here. The lower the loss, the better the model. If you're predicting a continuous number, you typically use mean squared error. But for large language models that are trying to predict the next token of text, cross-entropy is the absolute standard. Or if you're training embeddings, which mathematically pull similar concepts together and push different ones apart, you'd use contrastive loss. Cutting through this jargon really helps clarify exactly what the model is obsessively trying to minimize during that heartbeat loop. So once we know the loss, we need an optimizer.
This is the algorithm that actually turns the knobs. It moves the weights. Think of it as the motor. Plain stochastic gradient descent, or SGD, is great, but it can sometimes get stuck. So we often add something called momentum to help it roll out of flat regions in the data. For a really long time, an optimizer called Adam was the default, because it beautifully adapts to learning rate for each specific parameter. Today, though, AdamW, which adds a feature called proper weight decay, is the gold standard for LLMs. And as models get ridiculously huge, we're seeing more efficient alternatives like Lion and Sophia starting to step into the spotlight.
Right alongside the optimizer, we have the learning rate. This is absolutely crucial. The learning rate decides the actual size of our knob turns. If you nudge the weights too much, the model overshoots and completely fails to learn. But if you nudge them too little, training is going to take forever. Modern training solves this Goldilocks problem with a learning rate schedule. Typically, this means starting with a warm-up phase where the nudges are super small, followed by a cosine decay where the nudges gradually taper off as the model homes in on the perfect configuration.
Finally, let's hit Section 5, preventing AI from memorizing.
You know, an AI can sometimes act just like a lazy student. It'll just memorize the test answers instead of actually learning the underlying concepts. In the field, this is a massive problem known as overfitting. To stop it, we deploy a suite of safety guardrails, collectively called regularization. These techniques are honestly brilliant. Take dropout, for example. It literally shuts off a random percentage of neurons, maybe like 20% of them, during every single training step. This forces the network to not rely on any one genius neuron, ensuring the whole brain actually learns to generalize. We also use things like early stopping, where we just halt the training the exact moment the model starts performing worse on a separate test set. Oh, and data augmentation. This is where we artificially expand our data set, like rotating an image or paraphrasing text, so the model is constantly being challenged with slightly fresh examples.
Now, to tie this directly back to how you might actually use these systems, when companies like OpenAI or Anthropic do their massive pre-training runs, the models don't usually overfit. Why? Because they're being fed practically the entire internet. There's just way too much data to memorize. But if you are running a local fine-tuning job on your own specific, much smaller dataset, your model will absolutely overfit, for sure. And that is exactly why understanding these regularization tools is so incredibly important for anyone practicing AI today.
So we've covered the static weights, the nonlinear spark of activation, the looping heartbeat of the forward and backward pass, the optimizers that drive it all, and the guardrails that keep it honest. It all builds up to one incredible reality. Can you imagine trying to manage hundreds of billions of microscopic knob turns simultaneously, millions of times over, until a coherent understanding of human language just emerges? That's the sheer scale and the beautiful structured chaos of modern AI. Makes you wonder what we'll be able to train these models to understand next, doesn't it?